So the complexity of a language, i.e., how hard is the corresponding computing problem. Okay. So we're trying to define how hard is a computing problem, which is related to the complexity of a language, and what would it mean for a language to be complex? So remember what's our goal? Our goal is to take a set of strings, a language, a problem, becomes a language. Okay, and what's the goal? You're going to feed me an input W, and I have to say yes or no. So we can say the problem is hard or the language is complex if the task of saying yes or no to whether an input W is in the language, if that's a hard task. If it's an easy task, the problem is easy, the language is simple. If it's a hard task, the problem is hard, the language is complex. Okay? And what does it mean, a hard task or an easy task? Well, it's an easy task if we can build, let's say, a simple machine to solve it. It's a hard task if we cannot build a simple machine to solve it. Okay? So let's work with an example. So remember that push guy, that push light. So the language for the push light. Okay, remember now, the language defines the problem. You can forget about the fact that it came from the push light, but the language defines the problem. The push light problem is the language 1, 0, 1, 1, 1. Okay. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, and so on. Okay. And there's a very easy way to describe this set of binary strings, okay, which is all binary strings that end in 1. Binary strings ending in 1. Okay. So, is this a complex language? Is this a simple language? Is this a hard computing problem? Is it an easy computing problem? So let's see. Let's try to sort of build some, simple machine and see if it can solve this problem. So I'm going to build a simple machine. Okay. And I'm going to show you this simple machine in sort of a graphical way because we're used to graphs. It's another beautiful application of directed graphs. Okay. So, I'm going to imagine a vertex. Let me call this vertex Q0. And I'm going to imagine another vertex Q1. Okay. And, I'm going to imagine that my machine is represented by these two states, Q0 and Q1. So think of my machine as having two states. Okay. In some sense, I'm building a very primitive CPU. So I have two states. Okay. Q0 and Q1. Okay, and just like in any computer, but this is not a computer, this is just a machine. In any computer, you have, machine instructions. Okay, I'm going to represent my machine instructions, with arrows. Okay, directed graph. Okay, so, I'm going to show an arrow which, is linking Q0 to itself. So there's a self loop here. Okay, so it's a more complex graph than we have seen so far. So what does this instruction say? It says that, if you're in state Q0 and you happen to see a 0, stay in Q0. So if in Q0 and C0, stay in Q0. Okay. If you're in Q0 and you happen to see a 1, move, change states. Okay. Change states to Q1. Okay. Now, if you're in Q1 and you happen to see a 1, stay in Q1. If you're in Q1 and you happen to see a 0, switch states back to Q0. Okay, so if in Q0 and C1, jump to Q1. So move to Q1. Okay, now if in Q1 and C0, jump to Q0. Move to Q0. If in Q1 and C1, move or stay in Q0. Q1. Okay, so you can think of those as instructions of what to do in the event that you see zeros and ones. And why are we talking about zeros and ones? Because, the inputs to this problem, the input is a string of zeros and ones. Okay. Now, the point is, this is just a state transitioning machine with 4 very simple instructions. It's kind of like a vending machine in some sense. And so you might think that this is easy to implement as a mechanical device. So this is a very simple machine. A very simple machine. Now, what I'm going to do is I'm just, bear with me. I'm just going to color this, I'm going to put a sort of a green border around this state. So the way we will represent states like this. So some of the states have a green border. So let me just put a green border here. Okay. And I'll, from now on, not draw the green border, but just once, let me show you this nice colorful green border because I'm so good at coloring. Okay, look at that beautiful coloring, Bob Ross style. Okay, so here's a very simple machine with 2 states, the regular Q0 state and the green Q1 state, okay, and some 4 instructions. Okay, so now what's the use of this machine? So, well, let me also tell you that I'm going to start my machine in my state Q0. Now, what's the use of this machine? Okay, so let's consider some input strings to my problem L push. Remember what the task was. The task in L push was, if I give you a string, tell me whether or not the light is on. So if I give you a string, is the string in my set? Okay, so let's consider a few strings. Let's consider the string 0, 0, 1, 1, 0, 1, and 0, 0, 1, 1, 0, 0. Okay, so look, you can imagine that, associated with this machine is what we call a read head. Okay, so that's also not so hard to build. Something that can just look for inputs. Okay, so you can think that the read head starts here, the read head starts here. Okay, so now let's see what happens on this string. If it's so every time it sees a bit, it kind of gobbles it up and moves to the next bit. So it sees a 0. Okay, so it started in state Q0. It sees a 0, and it says if you're in state Q0, okay, stay in Q0. So it stays in Q0. Okay, so I'll put my finger on where the current state is. So I see a 0, I stay. Okay, I see a 0, I stay. I see a 1, I jump. I see a 1, I stay. I see a 0, I jump. I see a 1, I jump. Nothing more, I'm done. Okay, so at the end of this string, we will say that your state is green, i.e. Q1. Okay, let's see what happens at the end of this string. Okay, I see a 0, I stay. I see a 0, I stay. I see a 1, I jump. I see a 1, I stay. I see a 0, I jump. I see a 0, I stay. At the end of this string, I am in state Q0. Now I'll give you some exercises. Okay, figure out what happens with the following strings: 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0. Okay. Pause the video. Figure out what happens with all of these states. Classify each of these states into green Q1 or black Q0. Okay, 1, 2, 3, 4, 5. Okay, so you've done it. So I'll tell you, I won't even go through the machine because I constructed the machine. I know this machine. I am at one with this machine. Okay, so here you should have got black Q0. Here you should have got black Q0. Here you should have gotten green Q1. Here green Q1. Here green Q1. Here you should have gotten black Q0. Okay, and now what you will observe is a very interesting phenomenon. Okay, these strings which gave me black Q0, none of those strings, 1, 2, 3, 4, none of those strings are in L push. Okay, and the strings that all gave me green Q1, okay, and green Q1, all these strings are in L push. So when you run the string through this machine, by looking at where this machine ended up, are you in green Q1 or are you in Q0? Green for yes. Okay. If the machine ends up in the yes state Q1, you answer yes and you'll be right. The string will be in L push. If you didn't end up in Q1, if you ended up in Q0, you answer no. And indeed, it's the case that, all the strings for which you answer no will not be in L push. So what we say is that this simple machine simple machine solves the problem L push. Okay. Now, that suggests that L push is a very simple language. Now, for all the languages that we saw, 0 to the n, 1 to the m, palindromes, 0 to the n, 1 to the n. So some of the languages that we saw, you can go and see if you can construct a simple machine like this in order to solve the language, in order to solve that computing problem. Okay. We'll discuss this next time. Okay. But let's summarize. Okay. And this is the important summary of today. Okay. So we defined a computing problem as a decision problem. What is a decision problem? A problem to which the answer is yes or no. That means that we can, divorce ourselves from the actual problem and just focus on the yes set, the language that comprises all strings for which the answer is yes. We call that the yes set, and we defined abstractly a language is a computing problem. So you give me a language, you've given me a computing problem. We saw ways to describe languages, i.e. ways to describe computing problems. Okay. So we've seen in this class lots of computing problems, and we have a very precise definition of a computing problem. And then what's a complex computing problem? A complex computing problem is one that's associated with a complex language. And what's a complex language? Or what's a simple language? A simple language is a language for which you can easily test membership in the language. And why do we care about testing membership in the language? Because that's what it means to solve the problem. If I give you an input to my problem, which is a string, you should tell me yes or no. And if the language is simple, it's easy to tell me yes or no. Okay. And what we see here is that we can now start talking about the complexity of a language by how simple it is that how easy it is to construct a simple machine to solve that language. Okay. And then we might ask, well, what happens when the language gets more complex? Okay. So if a language gets more complex, maybe you can still solve it with a machine like this. You can think of this as a state transitioning machine, simple mechanical device that bumbles around from state to state. And somehow the ending state encodes yes or no. So there's a green state. Okay, well, you might not be able to do it with a machine that just has 2 states. Maybe you need 3 states. Maybe you need 4 states, 5, 6, 7, and so on. That means you need more resources to solve the problem. Okay, that kind of more complex computing problem where we talk about we need more resources, well, you'll study more about those kinds of computing problems in an algorithms course. Okay, but then there's another kind of more complex problem, okay, which is, is it possible to solve the problem with a state transitioning machine? Okay, if not, you need a totally different machine. You need a more complex machine. Okay? That's the kind of complexity that we are going to focus on. So we're going to ask the question, can all the problems we are interested in be solved by such simple machines? Or, if so, then we're done. We'll be done early with this class. Or are there problems that we cannot solve with such simple machines and we need a drastically new kind of machine with new capabilities and new power in order to solve those problems? Okay. So this is an example of what's called a model of computing, and that's going to take us deep into the whole, context of models of computing. So we're now moving into the context of models of computing. That's what's next. But before we can even talk about models of computing, we had to define what is a computing problem. Okay, and that's what we did today. Checking out.